Okay, so then let's see how we can get the properties of these wave functions representing matter waves. And for that, we will use the simplest form of this complex wave function written in the form of exponential. Okay, and okay, first thing, how about momentum? You know, for the matter wave, we have to use the de Broglie relationship, and using this de Broglie relationship, the momentum of the matter wave can be written as the Planck constant divided by the wavelengths. And for each of them, you know, if you divide by Planck constant by 2 pi, we actually represent using a different symbol like this. So H, we call it H bar, or actually it's German, so we can also call it H bar, which is actually equal to Planck constant divided by 2 pi. Okay, and then if you do that, now you need another 2 pi, and this corresponds to k. So therefore, now we can sometimes write the momentum to be h bar multiplied by k. Okay, and then now let's try to see. Actually, for this function, suppose you are actually taking a partial derivative with position. Then what will happen? This is a partial derivative, and this is an exponential function. So therefore, anything in front of x will come out. So what is coming out is ik. And then suppose you actually have this minus I h bar. Then you see that you already know minus I multiplied by I just becomes 1. So therefore, this becomes h bar k, which is actually the momentum, right? So what it means is that if you take the partial derivative in position and multiply by minus I h bar, then this momentum comes out in front of the wave function. So this mathematical operation actually works to get the momentum of this wave function. So therefore, this part, which is, we actually give it a name like momentum operator, which means that this is a mathematical operator. By using this, you can get the momentum of the wave function. Okay, and then next, how about total energy? You know, from this chapter, we learned that actually this is what Max Planck originally suggested, and it's for the light, but still works to any matter waves. So the total energy of this matter wave is Planck constant multiplied by the frequency. We can again rewrite using h bar, and in this case we have 2 pi f, which is omega. So therefore, hf is actually equal to h bar multiplied by the omega. This is the total energy of the light quanta, as well as the total energy of the matter wave. Okay, and then now this time, for the same wave function, now this time let's try to perform a partial derivative with time. Then anything in front of this time t will come out. So therefore, here minus I omega will come out, and then here you have I h bar. So therefore, again, you have this I and minus I. So therefore, it will become 0. It will become 1. So therefore, what you get is actually, okay, I should have written h bar omega, which is actually the energy. So following the same logic, this mathematical operation of taking the partial derivative in time and multiplying it by I h bar actually gives you the total energy of your matter wave. So therefore, we call this total energy operator. Okay. And then third thing, how about kinetic energy? You know, well, both in classical physics and quantum physics, kinetic energy is of course defined as a half of mass multiplied by the velocity square. And then this can also be written as a momentum square divided by 2m. And then we already learned that momentum for the matter wave is h bar multiplied by k. So therefore, what does it mean? In order to get this k square, what you have to do is that you can actually take the second partial derivative with respect to position. So let's try that explicitly. If you take the derivative with the position here. Now one time ik will come out, and then if you do it twice, another ik will come out, and exponential will not change. So therefore this, what you get is minus k squared. So therefore you have to multiply it by minus 2m haba square, then minus will disappear. So therefore what you get finally is this, which is exactly the kinetic energy. So therefore, following the same logic, you call this term, this mathematical operation, to be the kinetic energy operator. Okay, this is actually how we represent the kinetic energy, total energy, and momentum of the matter waves by using mathematical operators. Okay, well, one thing, I do not expect you to memorize this. Do not memorize. Do not memorize. Do not memorize. Just try to understand. In quantum mechanics, we use mathematical operators to extract momentum, total energy, and kinetic energies. We will see some examples later, but try to understand it instead of memorizing. Okay, I'm not going to give you any difficult calculations in which you have to memorize this. That's not my purpose. So please try to understand it. Okay, finally in this slide I'm going to explain to you the famous Schrödinger's equation. Okay, I think you have heard the name Schrödinger. He's very famous and he looks like this. So this Schrödinger equation is the way to understand how the wave function for the matter wave looks like. Okay, and then idea is actually very simple. You know, the total energy, even in classical physics or in quantum physics as well, must be the summation between the kinetic energy and the potential energy. And we learned that the kinetic energy is, of course, momentum squared divided by 2m. And here, of course, in quantum physics, we will use these operators that we have learned in the previous slide. Okay, let's try to see. Now let's say this is our wave function. So, and we learned from the previous slide, in order to express the total energy, we will use the total energy operator, which is operated on the wave function, right? Okay, this term is the total energy. And then the kinetic energy, we use the kinetic energy operator that we learned before. Okay, this is a one-dimensional expression, of course. And then you have to add it by this potential energy. Potential energy is something, is a condition in which the electron or matter wave exists, just like we exist in the gravitational potential of the Earth, right? And then this gravitational potential determines where we will be, and then how our potential is determined. Just like that, this potential energy term represents the condition in which electrons exist. So if you make a summation and perform the operation on the this wave function, then you will get the kinetic energy plus the potential energy. So therefore, actually potential energy operation is just like multiplying. Okay, and then now our wave function has the position term and the time term, right? And then if you perform this total energy operation, you are taking a derivative with time, and then we learned that haba omega will come out, which is the total energy. And then once you have finished this operation, now you can explicitly write that now wave function is the time term multiplied by the time term. And then on this side, now there is no time operation. This is only for position. So therefore, you don't have to worry about time. So therefore, you can just separate it out. Once you have done that, you can drop the time term. Okay, so we are not going to study how wave function changes as a function of time. We are not interested in it here. And then, okay, this term, which is the total energy, let's write it as E, because once the total energy is given, this is just like a constant. Okay, so therefore, now whole Schrödinger equation actually can be summarized like this. We can rewrite it using especially this second derivative term like this. So if you summarize it, if you take the second derivative with position of the wave function, this is equal to this constants, all kinds of constants multiplied by the total energy minus the kinetic energy multiplied by the function itself. Okay, so basically it's the second order differential equation. So basically solving the Schrödinger equation means that depending on this potential energy, depending on the potential energy and also the boundary condition, which tells you about what the wave function must look like at certain location. They are the conditions based upon which you have to solve the Schrödinger equation, and then the kinetic energy and the total energy will just come out during the process of solving this equation. Okay, and in fact, we know that the electrons actually exist in three-dimensional space. So therefore, for simplicity, we can write the Schrödinger equation in one dimension this way, but more correct way to write the Schrödinger equation have to be in three dimension. So therefore, wave function must be a function of x, y, z, and time. So therefore, now the kinetic energy actually includes three different terms. The second partial derivative along x and y and z, and potential energy will also be a function of x, y, z. Okay, this is actually more correct form of the Schrödinger equation, but this looks a little bit too difficult. So when you try to solve, we will only think about the one-dimensional case. Okay. Okay, as a last item in this chapter, we are going to solve the Schrödinger equation in the simplest possible case. The difficulty of solving Schrödinger equation depends on what kind of potential you have. And of course, therefore, the simplest case means that potential is simply 0. Okay. So in this case, now we can simply insert 0 in the potential term. And since the potential energy is 0, the total energy must be equal to the kinetic energy, right? So therefore, now instead of this total energy, we can insert the kinetic energy, which is p squared divided by 2m. And then now we can rewrite this by using simple squared form like this. And then, of course, this is about matter waves. So therefore, we will use the de Broglie relationship. So therefore, insert p, which is Planck constant divided by wavelength, to here. Okay, and then this is what you get. And then we know that 2 pi divided by lambda is actually the wave number. So therefore, or wave vector. So we can replace it by k square, and then finally get this form. So basically, solution to this second order differential equation should be something like this. If you take the second derivative of position in this wave function, what you get will be minus k square multiplied by the wave function itself. So what kind of function will it be? Of course, it should be something like exponential, because you take the derivative twice and you recover the same function, multiply by a certain constant, and then you took the derivative twice, so the k square comes out. So therefore, this exponential function must include k, but at the same time you have minus 1 here. So therefore, what is the square root of this minus 1? Which is of course complex I, right? So therefore, we finally figure that the solution to this equation should be either exponential of ikx or exponential of minus ikx. Try to insert it here and make sure these are the good solutions. And actually, the first one represents a matter wave probably moving to the right, and if so, the second term will represent the matter wave moving to the left. Okay, so and these two are equally good solutions. So therefore, because they are actually similar equations, so let's try to think about only one of them. So let's try to remove it and think about what this wave function look like. We have learned that this exponential of I something can be written as cosine of this thing plus I of sine term, right? So therefore, this wave function consists of complex numbers. So real term looks like cosine function, and imaginary term looks like sine function. Okay. And at the same time, the actual existence of electrons should be represented by the probability density, which is the absolute square of the wave function, which is again equal to the wave function itself multiplied by its complex conjugate, right? So you can simply calculate complex conjugate, and here what we assume is that C was a real number. If C was a real number, then you see that this exponential complex term drop, and what you get is simply C squared, which is constant and real number. So basically what it means is that probability density does not depend on position, so therefore it is equal everywhere. How? Because we don't have any potential energy. Because there is no potential energy, electron can be anywhere with equal probability. So therefore it makes sense. Okay, so this was the simplest case of solving the Schrödinger equation, and in the next lecture we will try to see the cases of a little bit more difficult but not too difficult. Okay, so that's what we are going to do. Okay, and let's make a summary. Alright, from this lecture we have studied the quantum physics, and we learned that light waves are actually quantized, and we called it photons following Einstein. And then we also learned that these photons have quantized energy, which is written as a Planck constant multiplied by the frequency. And we also learned that these photons have linear momentum even though it doesn't have a mass, and this linear momentum can be written as a Planck constant divided by lambda. Okay, and using this we learned that actually it satisfies the relationship of the conservation of energy and conservation of momentum when these photons scatter with the electrons. Okay, and we learned that actually just like light waves are particles, we learned that electrons are actually waves, which we call the matter waves, and its wavelength is given as lambda is equal to a Planck constant divided by the momentum, which is mv, and we called it de Broglie relationship. So what it tells us is that when something is not moving, the wavelength is like infinite, so it doesn't work like a wave, but as soon as it's moving faster and faster, the wavelength becomes smaller and smaller. Okay, this is how the quantum physics works. And then finally we learned how we can find out these matter waves for given potential energy, which is described by the Schrödinger equation. Okay, so we finally the Schrödinger equation is how we figure out the matter waves. So in the next lecture, which will be the last lecture in this semester, we will study more about matter waves. So actually we just learned that in the simplest case of having no potential, this wave simply becomes an exponential wave which exists everywhere. But then in the next lecture we will see how electrons exist in the case of simple potential wells, infinite potential well and finite potential wells. Okay, and finally we will see the Bohr model of atomic hydrogen, which is the case of the electron trapped by positive spherical potential. Okay, and this is how we understand the electron's existence inside the atom. Okay, so in the next lecture I will probably use a different method to record the online lecture, but anyway the method doesn't matter, the physics is the same. So I will see you in the next online lecture, and goodbye.